In this presentation, I'm going to be describing the conduction system of the heart. I'm going to be explaining the electrical activity in the pacemaker cells, which are in the sinoatrial node. This is how action potentials are created, and I'm going to explain action potentials in the ventricular muscle. So to start with, we are going to illustrate what the conduction system of the heart looks like. Alright, come over here. So, I'm going to draw our heart here. And this is looking at the anterior view of the heart. So we have our right atrium, we have our left atrium, and we have our right ventricle and our left ventricle. So let's go ahead and label our parts. We have our right ventricle. Alright. So our action potentials start out right here on the right atrium in the sinoatrial node. And this is commonly referred to as the SA node. We'll go over how those are generated after a while. So starts out here, and then it's going to travel over here to the left atrium through the Bachmann's bundle. And so that's a lightning bolt. Alright, so our electrical impulse starts here, our action potential starts here, travels over here through the Bachmann's bundle, and then it's going to travel to the atrioventricular node. And it is located right here at the top of the right ventricle. And this is our only electrical connection between the atrium and the ventricle. So this is our atrioventricular node. That's one word. I just made a space. Alright, and from once it gets here, this charge is going to pause. So we've got an electrical signal at the right atrium and the left atrium. These are contracting now, and our charge is paused right here at the top of the left or the right ventricle. So once the charge pauses, it's allowing these two to contract to force the blood into our ventricles. And we need our ventricles to have time to fill up with blood before they contract. So now this charge has been paused here for a second. Now it's going to travel over here to the bundle of His, and it's going to travel on either side all the way down, and these are your right and left bundle branches. So these are called your bundle of His. So our action potentials are going to cause the muscles to contract as they reach them. So this is our septum, and this is the first thing that's going to contract. So our muscle is contracting, our septum is contracting as it goes down, and this just provides a rigid bind in the heart. So the electrical impulse is traveling down each bundle branch till it gets down here to the Purkinje fibers, which are down here at the apex. So the septum is contracted, it's coming down here, and it starts working its way up and contracting on the way up. And this is going to force the blood out of the ventricles into the aorta and the pulmonary trunk. And as these are contracting and depolarizing, these have already relaxed. These are repolarized now, and the atrium have relaxed and blood is flowing back into the atrium to start the process over again. And so now our blood's going throughout the body, these are filling back up, and the process starts all over again. So the way that these electrical impulses and action potentials are created is they start out here in the sinoatrial node. And the sinoatrial node is completely independent from the brain. The heart is autorhythmic and it needs no brain function to be able to create its own action potentials. So, in a skeletal muscle, we have potassium on the inside, sodium on the outside. We have a positive charge and a negative charge, because these are negatively charged and negatively charged. We have positive concentrations of each. So when an action potential is created, sodium channels open, or they don't open, sodium comes into the cell, and then once they reach threshold, then the gates open and the sodium rushes in, and the potassium channels open and the potassium goes out. So now we have sodium on the inside, and we have a positively charged cell, and we have potassium on the outside, we have a negative charge. So that causes the cell to be depolarized, and then the action potential travels along, and these right here are going to repolarize, and the sodium potassium pump is going to switch these charges back around, and then we're going to have sodium on the outside and potassium on the inside again. And this just travels down and travels down, so it would look like this. These are positive, and as they depolarize, we are swapping these charges each time. And then we swap the pass along, we swap the charge, passes along, we swap the charge, and we do that till it reaches the muscle fiber, and we have contraction. But as this is happening, each one of these are repolarizing again, so these charges are swapping around. Alright, so the difference inside of a cardiac muscle is we have calcium that's in the mix. So to start out with, we have a resting membrane potential. And this is a negative charge. It's usually around maybe negative 70 millivolts or negative 90 in cardiac muscle. So right here we have threshold. And here we have a neutral charge. And then up here we have a positive charge. So let's say positive 70 millivolts, 0 millivolts. And for this one, let's say negative 38 millivolts or so. All right, so as our sodium creeps into the cell, it's slowly rising, and then it hits threshold, and it goes up rapidly. These sodium ions rush into the cell, and we are reaching depolarization very fast. And then it slowly, and at the same time, these potassiums are going out. So then we get over here, and we're slowly depolarizing, or repolarizing. And then we get down here, and we do the same thing again. Sodium creeps in, and then it rushes up, and then it repolarizes. So with cardiac action potentials, we have calcium that's in the mix. So there's our neutral, threshold, resting membrane potential, and positive. So in cardiac muscle, we have leaking sodium channels, and these sodium ions, they leak into the cell, and they do it by themselves. It's not like an action potential has to cause these sodiums to leak in. We have leaking sodium channels that allow that sodium to constantly leak in. Well, I say constantly. We have refractory periods that keep two action potentials from occurring simultaneously. So it leaks in, and it rushes up, and it's going to go up high into the positives. We'll say this is negative, or positive 70 millivolts. It's going to go above that, and then calcium is released. And this calcium causes these sodium channels to stay open. And the reason we need them to stay open is because if the sodium channel's closed, then they're welcome to have another action potential created while the muscle is still contracting. And we don't need our heart muscle to stay contracted, because if that happens, then, we're dead. So we need to give these muscles time to relax so that these sodium channels can close and repolarize and start over the process again. So this calcium keeps these sodium channels open until we repolarize, and then happens again, and then we repolarize. So this is depolarization. And this is the refractory period. / plateau. One thing I forgot to mention is when these repolarize, they hyperpolarize. And hyperpolarization keeps those cells from being able to receive another action potential right away. It makes it to where, we have time to finish the process of contraction before we start it over. So, scratch that out. And this is hyperpolarization. And then this is repolarization. And this is happening right here. This is autorhythmic. The SA node is autorhythmic. It beats automatically. And it is independent of the brain. So this allows our heart to be beating just as normal even if you're brain dead. So that's where ethics comes in, and it's kind of undetermined whether or not someone's considered dead when they're brain dead or when their heart's not beating anymore. Because you can make the heart beat outside of the body, you can't make the brain beat outside of the body. The brain work. So we have depolarization, we have our refractory period plateau, and this calcium keeps that open, those sodium channels open. So Na channels open, and then they close, and then we have the sodium potassium pumps, and they require ATP. So then we hyperpolarize, and then we come back up. We have calcium, keeps those sodiums open, and then we have hyperpolarization. So start here in the SA node, we travel over here through the Bachmann's bundle. Contraction occurs first in side of the atrium. Then our septum, and then all the way down to the apex, and then back up the exterior walls of the ventricles. And that is how we have a heartbeat. Action potentials come from the SA node, keep our heart beating, no brain activity involved. We have calcium in the mix, which differentiates it from a skeletal muscle action potential. And that's it. So now you know how the heart works. Happy Valentine's.